everyone, and thank you for joining this special guest lecture today in our course Musical Acoustics. Thank you as well those who are following us behind the camera, certainly from Oslo or other countries. Thank you for following us. Before introducing the very special guest today, I would like to thank the Department of Electronic Systems that has been very supportive to this, this talk and this special lecture. Thank you for all your help. Thanks. So, and now it's my big pleasure to introduce Professor John Chowning from Stanford University, the discoverer of the FM sound synthesis, and who is going to share with us today what has been 52 years since its development, as well as the FM's importance to him as both as a researcher and as a composer. So, welcome, John, to NTNU.
Thank you, Sarah, and thank you, the acoustics group, and the directors of the Dean and Peter for making it possible for me to be here. It's a great honor, of course. It's my first visit to Norway, other than transit in the Oslo airport. And so we have a long association going back to Sarah's stay at Stanford at Karma, and getting to know about this organization through Sarah and its support of our trip to China and the measurements that we made in 2018, 2017, yeah, and which was one of the great pleasures of my, post-retirement life. And so I'm here because I know something. You're here because you know something. Some of the things we know are the same. When I began, it was pretty basic stuff. And I'll review a little bit of that history so that we remember how this all began. What you know, those who are much younger than I, began at a level which was much richer, and so you know different things. What I can share with you is all the insights that came out of the discovery and development of FM synthesis. So I read in particular this phrase, "My naive discovery in 1967 of frequency modulation synthesis." I was not trained as a scientist or an engineer. I was trained as a musician. I knew about music. My whole education and passion was about music. And I didn't keep lab notes. I'm sorry, I did keep lab notes, but I didn't date my lab notes, as engineers and scientists are prone to do. So it was in 1967, I visited Bell Telephone Laboratories, where I met Jean-Claude Risset for the first time. He had begun his work with Max Matthews at Bell Labs in 1964, in the autumn. I began my work at the AI lab at Stanford, kind of in the back door, working at nights and weekends because it was unsponsored research. I never knew when exactly I just made the discovery. It was an ear discovery. But when I showed Jean-Claude, he wrote down what I had discovered from my notes, and he dated them. And there it is, the 18th of December, 1967. All I remember is that maybe 6 or 8 weeks before, I had done these initial experiments, which drawings and data are recorded here, it could have been this very day 52 years ago. Because right now it's about 3 in the morning, I guess, at Karma, or at Stanford. And it was late at night, and it was one of these magical moments where I realized that my ear had led me into something that was important. Never thought about synthesizers. That was not in the world in which I lived, nor in the pop music world at the time. Moog maybe is designing his first. Don Buchla had built a synthesizer about $5,000 probably, about 25 miles away. So it's ironic that I could not afford a synthesizer, but I could get access to a $2 million computer system. And that was lucky, and that has to do with the abstract nature of the idea of computers. This was the instrument which I used, and the only difference between that and the instrument that Jim Tenney had used that in working at Bell Labs with Max and others was that we made the pointer to the sine array pay attention to the sine bit, so that we could move forward and backward in looking up the sine table. The kind of labeling that I thought of was vibrato, vibrato depth, vibrato rate, which of course is the modulating wave, carrier frequency, modulating frequency, and deviation. This is the data for which Jean-Claude and Pierre Louis, who was a researcher at Bell Labs, an engineer, also from France, they wrote this data down. So that was the beginning. So I start off with that because of the timeliness of my presentation here and how it may have coincided exactly 52 years ago, but who will ever know. The beginning was the digital computer, of course, which is probably, of all humankind's machines, its greatest abstraction, because without program, it's nothing. So the designers of computer systems could not predict the extent and nature of the calculations their machines would be asked to perform. Max Matthews wrote an article in 1963, November 1963, The Digital Computer as a Musical Instrument, in which he writes, there are no theoretical limitations to the performance of the computer as a source of musical sounds, in contrast to the performance of ordinary instruments. At present, the range of computer music is limited principally by cost and by our knowledge of psychoacoustics. These limits are rapidly receding. He goes on, here, how can the numbers with which a computer deals be converted into sounds the ear can hear? The most general conversion is based upon the use of the numbers as samples of the sound pressure wave. A schematic diagram of this process is shown in Figure 1. So when I was given this article by a thoughtful fellow percussionist in the Stanford Symphony Orchestra who was trained as a biologist, having heard my accounts of my previous years in Paris, studying with Nadia Boulanger, where I encountered for the first time electronic music, some of which impressed me greatly. For example, Stockhausen's Gesang der Jünglinge, his great work Kontakte. I was not trained, as I said, as an engineer or scientist. And I looked at this schematic and I thought, if this is true, what he says, any perceivable sound can be generated by a computer as long as we assume that the loudspeaker is a source, maybe I can bypass all of the problems having to do with learning about electronics, learning about plugging wires into patch bays, and go directly through, if I could learn to program, to generating music from the imagination to sound. So that was important to me. That one diagram, which is the only thing I think that I understood in the whole article, having read it many, many times. There's something important else that he wrote, which was, intuitively we feel that if a high enough pulse rate is used and the amplitudes of the pulses are generated with sufficient precision, then any sound wave can be closely approximated by this process. Mathematically, it has been established that this conclusion is correct. This is the first citation in Max's famous article. Claude Shannon, 1948, reprinted in 1949. And in Theorem 13, if the base 2 is used, the resulting units may be called binary digits, or more briefly, bits, a word suggested by his colleague J.W. Tukey. So this is the origin of the word bits in the Claude Shannon's technical report, 1948. There's a wonderful review of the sampling dating back to the 1850s by H.D. Luke, The Origins of the Sampling Theorem, where he chronicles the lead up in conceptual thought about sampling from early telegraph and up through Claude Shannon's work. It's not primarily a mathematical article, but it's a wonderful brief history of sampling. The lab with which I was associated with the Stanford AI lab, it had a 1301 disk, a PDP-1 computer, which had a CRT display, which we used the XY ladder as XY, or channels 1 and 2 for our conversion system. So the process was to load IBM cards in a big 7090 IBM computer, bays of magnetic tape drives that would fill this room. It wrote its data, sample data from Max's Music 4 program onto the 1301 disk. Then we used the PDP-1, Digital Equipment Corporation's first computer, as a buffer. So we could read and write at the same time. And then the CRT as the converter, D-Day converter. So there's the system. What was wonderful, and its abstract attraction to me, was if I could learn to program the computer, everything else is constant. I mean, what we see here is exactly what we have in our iPhone, sampling digital analog converters, now A to D converters, of course, loudspeakers, exactly the same conceptual system. It's only gotten better and cheaper. This was the alternative. This was the Cologne studio. I saw pictures of this and I thought, when imagining myself trying to generate music for loudspeakers, which was my dream when I left Paris and went to Stanford, I'll never succeed because I don't have the skills, I don't have the access to such a studio. This is the Milan studio, where Luciano Berio worked. The men in the white coats scared me to death. The men in the white coats were the engineers, and they told the composers what they could and couldn't do. The men in the white coats. When I first made a presentation in Europe of Tyrannus, a piece that will hear tomorrow, with Ligeti in Berlin, before Ligeti took me to Darmstadt for his summer course, the engineers in the Berlin concert space would not lift the speakers up. I wanted them so that speakers were high enough so every listener had a line of path sight to each loudspeaker. The engineers told me that they don't do it that way. This is the way it was set up. And I said, well, I have to have it this way for these effects to work. They would not relent until Ligeti stepped up and said, okay, we'll cancel the concert. Then they put pedestals up and lifted the speakers. That's called the tyranny of the engineer. The engineer today is no longer tyrannical. Engineers are now our friends. We pay tribute to them. They pay tribute to us. Without them, we could do nothing. And it's a wonderful world that we all experience now in computer music, where this connection between the engineering sciences in the audio domain and musicians do nothing but enrich one another's lives. So this was Stockhausen's system for moving sound sources in Kontakte. So there were a rotating loudspeaker, 4 microphones on the table, and he spun the loudspeaker to create the rotational features of Kontakte. So a sine wave was first synthesized by digital means at Beltone Laboratories in 1957. There was computer music before Max's 1957 experiment. Alan Turing had the idea, but it was not based upon sampling. There was no digital analog computer at that time. He was making use of amplifying registers that were line printers in some cases, so they could create what they called computer music. But this is the first instance where a computer is used to generate a sine wave, which is a unit of perception. A sample is not a unit of perception. So a bit is to a number as a sample is to a sine wave, and a sine wave is a unit of perception. I say bit is to a sample because the famous composer Xenakis thought the sample was a unit of perception, which of course it's not. So Matthew's sound synthesis program produced this early So these little interruptions, the clicking, discontinuities, because they didn't have a buffer memory in this instance. So those were record gaps in the digital tape. Johannes Goebel, produced for Vergo the historical CD of sound synthesis, on which there are many examples of Jean-Claude's catalog of recorded sounds, his early experiments. Peter asked earlier about his effect of constant cycle or frequency offset between simultaneously sounding sawtooth waves, which produce an unimaginably beautiful effect that's on this CD. So I give this as a reference. This is Max in 1969, standing before the Bell Lab 1794. Max, who we owe so much, died April 2011, but he did not disappear because his legacy is huge. And his thoughts in those early days, as I will show you, persist in their richness to this day. So Max spent the last 25 years of his life at Karma, following John Pierce, who was his boss at Bell Labs, who provided the umbrella protection that allowed Max to work at this hugely important, rich establishment of scientific engineering brainpower on computer music. So Pierce, of course, was the inventor of satellite communications. The first Echo satellite, reflector, and then the second one, Telstar, which was active, the transmitter. He coined the term transistor. He was director of the research group, director of research at Bell Labs, and so he gave the name that the four other guys had invented. We owe much to John Pierce, who also spent his last days at Karma. So we had this incredibly rich resource out our hands, working with graduate students. We all learned from them both. And you'll see through this course of this presentation how important they were to me. This was my angel, David Poole. When I arrived at the computation center with a box of cards, which included Max's Music 4 program and the BFAP compiler that they used to compile it from Bell Labs, I was lost. How am I ever going to get this program going? The tuba player in the Stanford Orchestra, who was on my right, as I was the timpanist, was a very fine tuba player. I didn't know anything about what he did other than he could play the first invention by one line of the first invention by Bach on the tuba, which was pretty impressive. We talked about folk dancing, we talked about sailing, which we both loved, but we never talked about computer. So as I stood there with this box of cards, Dave Poole came to me and said, "What are you doing here?" And I said, "What are you doing here?" And I explained, and he said, "Maybe I can help you." And he was at the time taking a course with John McCarthy, the master artificial intelligence guru with Marvin Minsky at MIT, and the inventor of the language Lisp, of course, many other things. And Dave was a real hacker in the good sense, as we used to refer to hackers as people who could get down into the bits and the bytes and look at core dumps of zeros and ones or octal and figure out what was going on. Dave taught me everything. He taught me what a function was. He tried to explain how a bit worked. It's like a light switch. Okay, well, of course those are electrons. What's an electron? He said, "John, at some point you just stop asking questions and believe me, 0 and 1 is on and off." So to him I am indebted. Max was the one who gave me the idea and the means, but Dave Poole was my angel, a treasure in my life. He died in a sailing accident in 2001, overwhelmed by a storm in Glacier Bay in Alaska. He knew how I felt about him and my debt. So FM came about because of my interest in trying to recreate in program what Stockhausen had done, but I realized that I could do better because the program allowed me to bypass the engineer. I didn't need interpreters. I needed lots of help. It was in 1966, I just expanded my scope from stereo to quad. And I wanted to create moving sound sources in a generalized form. one of the engineers at the AI lab suggested that I use vector algebra. And I said, no, I'm sorry, I don't understand vector algebra. I don't have that kind of background. I wanted to create Doppler shift. And I realized that I could solve these problems graphically. So here's what I did. They named the channel 1, 2, 3, 4, according to the Cartesian coordinates, because there was no standard at those days. The listener space was within the perimeter of the square defined by the position of the loudspeakers. The illusory sound space outside the perimeter. So, a source at a certain distance, which is a radius, and at a certain angle. So, azimuth, distance, plotting points at a constant rate with a kind of mouse, which when the button is depressed, plotted points at a constant rate, and so therefore preserved in the distance between points was the radial velocity. And all the while, I'm surrounded by engineers, scientists at the AI lab, including speech scientists, computer scientists, linguistics, psychologists, all of whom knew the answer to every basic question that I asked. Help me understand the Doppler question, no problem. Tell me if what I'm doing right, looking at the difference between distances, I am in preserving the Doppler shift. Yes, you are. I could go to any one of them to ask any question and receive a reliable answer. I just couldn't go back to the same person twice. That was the rule. But there were lots of them, so I could go to other people. And I pursued this kind of incidental education until I understood a lot about acoustics, a lot about computing, a lot about scientific thinking. And I did what Stockhausen could not have done. I created a program that produced arbitrary sound sources. And the program would automatically draw the functions controlling azimuth, distance. The distance cube was a mystery, and I think that I nailed it, having understood with my ear that it had to do with reverberation. And it was one of the, I think, my most important discoveries in the domain of perception from these years. So I realized that a well-written program could produce not just a circular path around the listening space, but it could produce arbitrary patterns. With the light pen, I was drawing some curves. One of the engineers looking at the display said, that looks like a Lissajous function, Lissajous figure. I said, what's a Lissajous figure? And he explained what a Lissajous figure was. So I created some complicated Lissajous figures, which I used in Tyrannus, which is a piece that we'll play tomorrow. So I make this reference, all using FM synthesis, of course, because in this example, you will hear a kind of distinct attribute of sound moving in space, which is not unlike that which happens in nature. Oops, sorry. Begin again. That the sound speeds up and decreases. As it approaches a change in direction, the sound source, the velocity decreases according to the way the we move through a sine table as the slope changes at the peaks and valleys. So now let's, Tyrannus, the name derives from natures. Let's listen to again. I'm sorry. That's without sound. Oh no, see, my hearing is so poor I can't. Okay, now let's look at an object moving at a constant rate. So it doesn't decrease in velocity as approaches change in direction. And now we listen to the two together. The red line is the lisigou, true, speeds up, decreases in velocity, then catches up at the end, they end together. So this is a small distinction. The object, the ball that moves at a constant rate, is like computer games work, But this is a musical moment from my point of view, a nuance that is important in the listening experience to which composers, musicians pay attention. So it's not unlike what happens in a skater who rolls into a curve and accelerates and then has to pick up speed. And so lisigou figures these patterns are not unlike a mass in motion in nature. This is the system which I conceived to realize these. Well, it's a bit complicated, but I don't want to explain it, but I'll leave this slide set, Sarah, so anyone who's interested can look in detail. What was important was my realizations at this point. Computers and languages allowed direct control of the material of music. Sound structure and music structure can be joined in a new way. The value of multidisciplinary environments. I listened to the description of the acoustics group at this university, and it seems well populated by many different ways of thinking, people thinking about acoustics, and which is, in my view, one of the most important attributes of an educational institution. And my ears are my most important tool. Okay, I'll sum up my research in distance, in spatial projections in this five-dimensional space. Okay, loudness and distance are subjective. Intensity and frequency are objective. Good, solid, scientific quantities. So when we change one, for example, to make a sound softer, we decrease the centroid and bandwidth of the sound. That is, less energy in the system. So the centroid and bandwidth go toward the lower end. If we make a sound higher, but loud, and now make the distance increase, we get the following effect. So the reverberation is constant. The direct signal decreases according to the inverse square law. So in the reverberation is preserved the energy at the source. because the centroid and bandwidth do not change. However, if we now, at the same beginning point, decrease the effort or the energy in the system, we decrease the centroid and bandwidth, and the reverberation decreases in the same proportion. How we compare the endpoints of the two. See, close and soft, loud and far. Again, a very subtle difference, but nuance is what music is all about. And in my music tomorrow, you will hear many examples of the distance cue, sounds that begin distant in space and are transformed as they pass through the space or around the space and out the other side. Metamorphosis. Now, so constant reverberation, but the signal decreases according to the inverse square law. So this image, which I built in 2005, and is certainly the most complicated PowerPoint animation that I've ever tried, was my conception of loudness distance by the time I composed Saboleth and Tyrannus, these two of those pieces that we will play tomorrow. So here's the simple explanation. Matthew's my subject. I clap my hands. Direct signal goes to his ear. The signal is a spherical wave that bounces all the collection of echoes arrive at his ear a short time later. Now, I clap softly at the same distance. So the direct signal decreases according to decrease in intensity, as does the reverberation. But if I double the distance, clap, drop my water bottle, and no, it's okay. So if I double the distance, the inverse square law says that the intensity will decrease by 1/4, but the reverberation doesn't, because the same amount of energy is in the room. So that's how I believe we make judgments about distance and loudness. They're coupled. And this was one of the insights that came out of my work in these early days. The distance cue was dependent upon a signal that had internal dynamism. Because if you use a simple sinusoid, the interaction of the direct signal and the reverberant field are such that the ear can't just make a distinction between the two. But if you have some change in frequency, for example, to which the ear is very, very sensitive, small differences in changes in frequency, then the interaction of the direct signal mixing with the reverberant signal, on which Matthew depends to make his judgment, is distinct, and he can separate one from the other. So, looking for sounds with internal dynamism, I discovered FM synthesis, which provided powerful control over bandwidth and centroid of the spectrum. Okay, here's the simple, typical the distance cue implemented, say, in a synth. What do you call a synth? Yeah, with synthesizers and reverberators. So you scale the distance control after you've taken reverberation, a fraction of the reverberation from the direct signal, the sound source, and send it to the reverberator. So the loudness cue at the sound source determines centroid. The distance controller affects the mix of direct or reverberant signal. Okay, in November 1967, I was fully engaged in the refinement of the perceptual cues related to spatial illusions of sounds in space. Intuitively, I knew that the saliency of the distance cue was dependent upon finding ways to create internal dynamism of computer sounds. My work in spatialization was dependent upon reverberation for the distance cue as demonstrated above. Experimenting with vibrato rates and depths, I increased both, not knowing anything about the FM equation. This was an ear discovery. Okay, so here is the discovery of FM synthesis, a kind of quick synopsis of what I went through this long night, beginning probably at midnight until 5 in the morning. Notice that the text for this was written in gold, because ultimately, decades later, 67, 77, almost 20 years later, it began producing big income because of the license to Yamaha. Okay, so we begin with the sound at 200 hertz. For me, that was my center frequency. Hertz, okay. Plus and minus 100 hertz. Now, engineers and mathematicians will realize that that ball tracing is not following, its velocity is not tracked according to the real sinusoid. It should slow up as it hits the peaks and valleys. But I didn't know how to do that in PowerPoint, so this is what we got. Okay, so once more, plus and minus 100 hertz. This is linear modulation. Now, plus and minus 200 hertz. Because now I'm thinking, experimenting, well, if I keep pushing this, am I going to break the computer? And realize, no, of course I won't. And so I increased the rate from once per second to 2 times per second. I'm tracing this still in the time domain, right? There's a change of pitch through time. How about 20 hertz? It's ambiguous. Am I tracing it, tracking that now through time, or are we in the frequency domain? Now at 40 hertz, clearly it's in the frequency domain. So I thought, this sounds like something rich in harmonics. How about 200 hertz? That the rate at which center frequency is now deviating around that frequency plus and minus 200 hertz. What will this sound like? That's the same pitch as I began with. And I knew that there was something important because I knew what it took in 1967 to produce a complex wave. Additive synthesis, as Jean-Claude Risset worked, had to have an oscillator for every partial. And I was producing a complex wave which had more than 3 or 4 harmonics. In fact, I know it was probably about 5 or 6 with this deviation, and was doing it with 2 oscillators. Okay, so the long night progressed, and I tried many, many different combinations, and it transposed. If I transposed everything up an octave, it followed what my ear would have expected. If I changed from harmonic relationships between the carrier modulator to inharmonic. It transposed. So I asked Dave Poole, look, what am I doing? And he said, I don't know, let's go look at a radio engineering text. He sort of knew it had to do with FM synthesis. And what fell out was, my center of frequency was the carrier frequency. My modulating frequency, which I called the deviation frequency, was the modulating frequency. Delta F was the deviation, that was frequency deviation, and from that we derive what's called the modulation index, which is delta F over F sub m, modulation index. This is the equation. This is the trigonometric expansion. And this was in the basic description of FM in Frederick Terman's radio engineering text. And Dave said, this explains exactly what you're doing. Now, I think it would take a pretty good work of a mathematician physicist to derive the trigonometric expansion from the basic wave computation. It involves Bessel functions. Bessel was a 19th century naturalist who derived Bessel functions when he was looking for planetary motion, I think. And the FM equation and its derivation was by Anderson at RCA Labs, I think in 1929. Anderson, maybe. But I think it's not I think it's a pretty complicated derivation to move from what's actually computed, a simple equation, and what explains, because nowhere in the computation are there Bessel functions. They're inferred. So, typical spectrum of FM sidebands in radio engineering texts, again, right out of Terman, of a carrier frequency. Its amplitude coefficients are determined by the J0 Bessel function. With a modulation index of 1, we have upper and lower sideband components. So the index now interacts with J0 such that it's reduced to about 0.9 amplitude. The second Bessel function, J1, determines the first amplitude of the first upper and lower sidebands. And the third upper and lower sidebands. And finally the fourth, and beyond that they become insignificant. So in general, as we increase the index, we increase the bandwidth of the signal. Pretty straightforward. So there's a signal where carrier frequency at 500 hertz, the modulating frequency is 100 hertz, modulation index is 0, so this is what this one sounds like. But let's look at the equation. Notice that the odd-ordered lower sideband components have a negative sign. Thank you, Sarah. So therefore, a negative sign means a phase inversion. What's it sound like? The same, because the ear is insensitive to phase in these conditions. But why does it matter? Didn't matter to radio engineering because their carrier frequency in the megahertz. But we realized that it matters in FM synthesis for this reason. The modulating frequency remains at 100 hertz, while the carrier we changed to 100 hertz. So now we have sidebands that are in the negative frequency domain. So what's in the negative frequency domain, positive, we change its sign and place it in the positive frequency domain. So it was minus 100, sine minus theta equals minus sine of theta. So it's now, we take the algebraic sum of the two, so we subtract from the 100 hertz and add to the one at 200. What's this sound like? Same pitch, but different timbre. So that's why we have to pay attention in the precise description of how this works to these lower sideband frequencies in the negative domain. In fact, in usage, since the most interesting FM use is always everything's changing all the time a little bit, we don't really pay attention to it. But just to understand the theory, in harmonic spectrum, we change the sign. Now, we're going to add or change the modulating frequency from 100 hertz, change the carrier frequency to 100 hertz, and now the modulating frequency from 100 hertz to the golden ratio times the modulating frequency, which is about 162 hertz. So now let's listen to we have to flip the signs. Okay, notice that when we flip the component at minus 62 hertz, it doesn't fall on one of the upper sideband components, nor does the next lower sideband frequency and the last. They fall in between. So what does this sound like? Clearly inharmonic, because pitch is ambiguous. But it's orderly. Now, what's interesting is we make amplitude and index a function of time. So here we see how the amplitude of the carrier component changes with change of index. Now with all sidebands, a surprisingly simple auditory result. So when I first did this, I thought, that sounds like a diphthong. And we'll see later how that turned out to be important. Okay, so about, let's see, 1967, I developed, perfecting my spatial illusions. By 1969-70, I had developed these following tones. Carrier frequency and the modulating frequency are related by the square root of 2, modulating frequency square root of 2 times the carrier. with these functions in amplitude of index and amplitude of the envelope. So the modulation index and the amplitude envelope are determined by the same functions in time. Well, it makes sense. In harmonic spectrum, at the onset, lots of energy, lots of partials, and as time they decrease, when the index hits 0, we have a sinusoid. The amplitude does the same. So the centroid of the spectrum goes from high frequencies to low frequencies. Using the same ratio of carrier to modulating frequencies, now with a function where the modulation index is initially high, quickly goes to 0, but the amplitude envelope kind of peaks after the index hits 0, so it's like a sinusoid, like a resonance. Damped. And here's what it sounded like. Now point out that the time constants for each of these tones is determined by pitch height. So the lower the pitch, the longer the tone. The higher the pitch, the shorter the tone. But they're pretty impressive. Brass-like tones. When I showed Jean-Claude, 1967, his first experiments with FM synthesis, he showed me the work he had done in synthesis of brass tones, using additive synthesis and analysis program. They had it at Bell Labs, which did a pitch synchronous spectral analysis for. And he determined that during the attack portion, the harmonics increased from low to high. So I reflected on this in 1969 or 70 maybe, and realized that if I make the modulation index and the brass tone envelope the same, I could perhaps simulate brass-like tones, and this was the result. So during the attack, of course, the Bessel functions were sweeping through them, and there's this complicated amplitude modulation, which was not controlled by the user, but it happened to fit the kind of complex change in energy that Jean-Claude Risset had observed in his pitch synchronous analysis. And this was the result. So, higher blast tones, then mid-range, then lower, to follow, it was transposable. It seemed orderly. A colleague at Colgate, Dexter Morrill, looked at my work, these early simulations, and he's a trumpet player. And by introducing pitch skew and a little bit of vibrato, random vibrato during the steady states, he produced these remarkable FM brass tones. Everything's in motion always. And listen to effort. No. So So how did he do that? How did he get this feeling of effort at the high note? By moving the centroid of the spectrum to the right. So it's simply true in nature that effort is related to centroid. A violinist presses harder on the bow, increases velocity, it moves the centroid of the spectrum to the higher partials, higher harmonics in that case. A percussionist with increased strike force, same thing. The trumpet player, effort is reflected by the overall intensity and the position of the centroid to a relationship to the known reference, which is brass timbre or trumpet timbre. So we have to have a reference, which is our listening experience, our knowledge of music, and or listening, really not so much knowledge, but the ear experience. The mother who speaks to an infant child who's sucking a bottle in the presence of other mothers, all speaking at the same dynamic, the child identifies the mother's voice as indicated by her entry into the acoustic space, into the room. The child stops sucking, notices, okay, that's mom. This was done at Stanford in 3-month-old infants. If the mother's voice increases a little bit, expressing anxiety, it's a motion of the centroid. So we learn this from early age about nature because it has to do with survival. Metamorphosis. When I made these examples of brass tones in 1970, I think it was, M.C. Escher was all over California. There were M.C. Escher T-shirts and posters everywhere. This idea of metamorphosis, and I thought, I have this powerful means of synthesis where I have a huge spectral space, timbre space, and a very small parameter space. So here's a timbral metamorphosis of kind of a snare drum, noisy sound that over time becomes a trumpet sound. This you will hear in context in Sampling tomorrow. So the pitch frequency begins at a ratio of 1 to whatever pitch I'm producing, which are different pitches. The ratio of the FM to the modulating frequency at the onset is square root of 2, so it's inharmonic spectra, with a large index, which means aliasing from both the half sampling rate and around 0. And over time, the pitch frequency ratio becomes 1. And the modulation index from 2 to about 3 or 4. So here's the example. Okay. The sound is better than what you will hear at the concert, but that was pretty amazing for 1971. Here's the Bessel functions as I created in one of Apple's programs. The useful area in general is, whoops, that's not supposed to happen. So, the power of FM synthesis determined about the time that Yamaha first became interested. Processor speed was efficient computation, simple sine wave modulated by a second sinusoid. Memory, few stored functions, 1/4 of a sine wave from which the other 3/4 were derived. And piecewise linear envelopes, so we had to generate the brass envelope. We didn't use a curve, we used a few points to define piecewise linear approximation. Aliasing, which was a huge issue and it was determined by one value, the modulation index. So as attractive to Yamahas, they increased pitch height, they could decrease the index and avoid the problems of aliasing. The musical power, few but perceptually salient parameters, time-varying spectra, dynamic spectra, both harmonic and inharmonic spectra, simple coupling of intensity and bandwidth and or centroid, center of mass of the spectrum. So in 1973, the Office of Technology Licensing identified Yamaha as the largest producer of electronic musical instruments in the world, organs primarily, and a few beginning analog synthesizers. But their footprint in the United States was very small. They were known for their pianos. The Office of Technology Licensing had contacted Hammond, Lowry, Wurlitzer, the big American oil organ companies, all of whom sent engineers. I would show them the program that I had written, played the examples, and they would look at me and say, how many chips will it take to do this? They're thinking analog. I said, I have no idea. This is what I've done. Then OTL kind of, at the last desperate moment, put a business student on the problem. He determined that Yamaha was producing all these instruments, but mostly in Japan. They sent an engineer to Stanford. I explained what I was doing. In 10 minutes, he understood exactly. They were already working in the digital domain, thinking far ahead. So here I am, my first trip to Japan, standing next to the young engineer to my immediate right, Hiro Kato, and to my far left, Aki Endo, the two guys who built probably the first real-time synthesizer, digital synthesizer that was ever built. It was, breadboard, of course, and the input was a PDP-11, which Hiro Kato, generating control functions. The other guys were accomplices. So I say now publicly, DX7 was not an invention of John Chowning. It was the invention of about 100 really good engineers over a period beginning in 1973 to 1983, who developed the DX7 based upon my many visits, exchanging where I shared everything that I knew about programming and creating voices. This is kind of a presentation that Hiro Kato made many years later, showing some of the work. And let's see what's important. Frequency modulation is by far the most important algorithm synthesis method at the time. This is Max, to whom Hiro Kato made reference. Some of their implementations, 1975, Pierre Boulez and the whole IRCAM team came to Stanford. Let's see, that. What am I doing? Yeah. So Pierre Boulez is at the light pen. That's the system with which I drew my first list of curvilinear forms, which then someone convinced me Lissajous figures were better. Andy Moore with the long hair, I with the checkered shirt, Max Matthews to my left, and Steve Martin, a young graduate student who was showing Pierre Boulez how to use the light pens. Oh, they're the names, I'm sorry, I forgot. Okay, now, spectral modeling. It's a recording of a real singer singing a crescendo. So notice at the beginning, in white, the spectral energy is around the first and second harmonic, but at the end of the crescendo, it shifted to the seventh harmonic. Beginning, end, beginning, end. The waveform, you can hardly notice any change at all. So the change in actual intensity of the overall waveform is unnoticeable. So when we produce an increase of, vocal pressure through the breath pressure through the vocal folds, you can hear the energy shift to the higher resonances, formants. Okay, so beginning and end, spectral modeling. Remember this one, index of 1, where the carrier is a multiple of the modulating frequency. That looks a lot like that part of the final crescendo, of end point of the crescendo. This, whoops, they should be folding on, there, should be that. This looks a lot like this part of it. Okay, so we put these two together. That takes two carriers, make them log frequency, and we have a good match. So this is spectral modeling. So all the instruments that have strong resonances can be modeled by a modulating frequency at the pitch frequency and the carrier frequency at the closest harmonic, at the harmonic closest to a desired formant. Building a singing voice based upon Johann Sundberg's formant data. At IRCAM in 1968 and 69, I wanted a project, and I thought I'll try to create an FM singing voice. Johann Sundberg was there at IRCAM in another project. He is a great scientist of our lifetime. There's no one surpasses his work in understanding the singing voice. He's generous, and he shared generously. Here's what he provided me. Found in the Source of Singing Voice, Northern Illinois Press, 1987. But at this time, it was just a paper, and he gave this information to me. So for the vowel phonetic A, the spoken A in circles is constant at that formant is constant at around 3,500 hertz. But the sung vowel changes with pitch height. And so the third formant, the second formant, and the lowest formant. Now, I cast this in log frequency because it's easier to see. Now just the three lowest formants. And you see that the formant frequency of the lowest formant is constant for the vowel A to about 400 hertz. Then it locks in to the formant frequency and tracks it. The first formant is not allowed to be lower than the phonation frequency, the frequency of the vocal folds. The spectrum of a female singer at frequency G3. Now with the fundamental frequency an octave higher, the resonances are not at all clear, the formants, because there's not enough spectral density. And when a female singer increases the pitch, the lower formant increases as well, as we saw in the lower formant trajectory. So we mark what we hear in red. How to determine resonances when partials are sparse. Sundberg asked the soprano to sing a tone, then stop the phonation and freeze her tongue-jaw positions while a harmonically rich buzzer was held to her throat. Providing a sufficient density of partials to reveal the formants. Ingenious. A very good soprano, and because Sundberg is also a singer, there was a good relationship between artist and scientist. I think I have a better slide of that. This is, so the buzzer frequency fills the region. He can now figure out where the formants are of this trajectories at that pitch. So those are the formances and resonances. So this is what we hear. Having resonance formances when there's vibrato. This is what's acting. So there's an asynchronous modulation of the amplitudes of the spectrum as they climb and fall away on the walls of the resonance. This is the instrument which I use to produce my female vocal tones. Okay, for each carrier there's a modulator, which is there. So there are 3 carriers, 1 modulator. The modulating frequency is always the pitch frequency, phonation frequency. The carrier is determined by the formant, the harmonic closest to the desired formant. But the real subject of interest is in the detail of the micromodulation. So the random, I can see, piecewise linear random function set at about 1 to 2% of the fundamental frequency and is scaled to loudness. So the louder, the greater intensity, then slight increase in the random deviation. So there's the function. A sinusoidal vibrato is set at 4.7 hertz on average and scaled to loudness. So the louder the voice, usually a soprano sings greater vibrato. Ah, ah, right? And then skew, a little portamento during the attack, which is always contextual. So the skew is added to the complex. These 2 functions are summed together, and we have but a believable vibrato. The harmonics of the singing voice are modulated by the resonances. This is what we hear. This is what we infer. The carrier frequencies are determined by the harmonic closest to the resonance. So the carrier 1, carrier 2, carrier 3. In the next audio example, we'll hear the 5 vowels. For each pitch, the 3 frequencies are calculated according to Sundberg's vowel trajectory. Left. Okay, Boulez heard these because at EarCom in these days I was working in the early morning and this big soundproof door opened. He peeked his head around and he was with the great choreographer Maurice Béjart. They've been having a conference at his desk because there was no audio switch. Everything that came out of the computer was broadcast to every office. He heard them, came down and asked me about them, and it was the only time I had a really solid talk with Pierre Boulez. He asked if they were recorded or how I was doing this. And then when I explained to him that these were synthesized, and he went on, wanted to know the details, etc. Okay, so let's decompose the singing voice. We hear a fundamental, followed by all the harmonics that would be present for a sung vowel. And then at the third stage, the micromodulation, which is applied synchronously to all the harmonics. Fundamental. Doesn't fuse. Sounds like an organ stop. And then magically, it becomes identifiable as a singing voice. This became a famous example because until this example, digital domain, we didn't have this kind of control over precision that we could reveal such an important attribute of the singing voice. So the point is, there are errors in the functional nature of the singing voice. No soprano can hold a pitch absolutely constant. No soprano can make an absolutely even vibrato. So the bel canto style of singing is based upon learning how to control these and minimize the way one corrects. You don't correct immediately, you slide into the corrected pitch. And you learn to control the voice. Breath pressure, of course, minimizes these, but there's always some random component. It's just in the nature of the physics of the instrument, whether it's a bowed string, trumpet, whatever. It's part of nature, and our ear depends upon this fusion and this micromodulation. And it was revealed in this example. So it reveals source identification. I would like to see a real-time brain scan of what lights up, what regions of the brain at the moment a listener hears this kind of abstract dull sound turn into a singing voice. All right, a thorough examination of this based on this example that I made at EarCom became the doctoral dissertation of Steve McAdams, who's now at McGill, when he did his dissertation at Stanford. source identification. Now, in principles of perceptual organization, Gestalt, proximity, symmetry, I've got to move along here. Similarity, continuation, and the closure, and the most important is common fate, which is mediated through time. Okay, so don't blink. So we organize according to grouping, that which distinguishes itself. So there we are. And the image disappears. So how can we demonstrate this? We'll make 3 sopranos, all of whom fundamentals are 400, 500, 600 hertz. So the implied frequency is 100 hertz, right? Because of their common harmonics, and all of their harmonics, without any way to differentiate, we can infer 100 hertz pitch. Unless we, without color to separate out, we cannot see the difference. Without common fate, we can't hear the difference. So when each of these tones begins to be organized according to common fate, where each group is synchronous, but it's asynchronous micromodulation between the 3 groups, this is what we hear. Can the ear see the 3 voices? 4, 5, 600 hertz. All the harmonics, 100 hertz. Now we hear 3 voices. So that's source segregation. Now, same example with another. Look for those 3 singers. And they disappear into the miasma. Phonae and voices are rooted in idea-structured spectra, first elaborated by John Pierce in an 8-tone canon. In his work Mutations, we say define the relationship of pitch, of timbre to pitch, where sets of pitches also become the spectral components of a sound, yielding a magical, never before heard, functional relationship in the pitch-timbre space. Jean-Claude, as I told you at the outset, was my close colleague. We worked and shared together through our whole professional lives. He died in 2016, too early. This is the last photo I think we have of Jean-Claude, Max Matthews, and me together. But here's the example. Melody becomes harmony, the same pitches, but now with a swell, we hear it as a harmonic relationship. And then the same pitches are used to sound a bell tone, gong-like tone. Whoop. Oh, my synchrony is off anyway. So here's the example that we've just heard. Now I'm going to impose upon that an envelope over the fundamental that looks like this. So it begins as a partial, as a bell tone, becomes a singing voice. Put all those together. Another view. Now, In the pitch space, a gong or bell-like tone becomes a set of singing voices. So this is a timbral interpolation from single timbre to many voices. Timbral extrapolation, using the same model of 3 carriers and 1 modulator, we increase the low energy frequency in a male voice as if the lowest resonance was because of a meter-long neck and a great big pumpkin head, and we produce the same, this example. So basses don't sing this loud, this low. Basses can sing low, like Tibetan monks. So this is my, okay. The opening of phone, where gongs become voices, low gongs become middle lane voices, and very low gongs become basso, Prof, and DC main. Okay, well, we'll hear it tomorrow. And now I want to jump to one demonstration, and then we'll stop. This is a remarkable demonstration because when we do experiments in new music, the context is new, the experiment by nature is new, so there's no strong reference that will confirm what we believe to be true. This is an example that was done in 1989, I believe. Tones and tuning with stretch partials. Of a well-known chorale. So one of the pieces that we'll hear tomorrow is Stria, which is based upon the ratio of the powers of the golden ratio as carrier modulating frequencies. And it produces a very structured but inharmonic timbre. And I always wondered if it worked because of the nature of the complementary relationship between spectral space and the pitch space. So the pitch space has common frequencies. And I came upon this example which was done by Hoeksma, a famous Dutch acoustician, to confirm John Pierce's 8-tone canon and its meaning having to do with basically here's the example. Pitch space. So I made this slide. Pitch space, common practice tuning. Spectral space, harmonic series. This is the example. This is done with additive synthesis. For every partial, there's a separate oscillator. Okay. Now, they changed the pitch space from 2.0 to 2.1. That's 10% difference. And they stretched it so that now notice that the first The fundamental is at the lower octave exactly, but the second harmonic is somewhere near the major seventh. The third harmonic is somewhere near the what do we call it? We call it the diminished fourth, or diminished fifth, or augmented fourth. So what's it sound like? Okay. Expected, right? Because the harmonics don't coincide with the pitch space. Okay, and it doesn't get better. We could go up. Okay, now we restore the pitch space to 2.0 and change the harmonic space to 2.1 to the log to base f. So we stretch the harmonics. Now the second harmonic is somewhere near the minor ninth. Okay. So what does this sound like? So that doesn't get any better either. Okay. So what happens if we change them both? Stretch them both. Well, is it going to be twice as bad, of course. Except if we look at the stretch, we'll realize something really, really important, that the second harmonic falls at the octave, the third harmonic falls at the stretched fifth, close to, the fourth harmonic exactly at the second octave. So what's it going to sound like? I did this, this is not what they tried to prove. The term I was trying to think of was critical bands, how acoustic perceptual dissonance happens. So this demonstrates something because listen to it. Sounds pretty good to me. Let's listen to the original. So it doesn't get worse. The original. Sounds synth perfect, which of course it is. So in a way, my preference is for the 10% is a lot. That's like almost a whole tone. So is there room for play? We know at some point it'll break. Will it break it? We change them both to 2.2. We know that between 2.1 and 0, it'll all work perfectly well. At what point does it break? No one knows yet. It's a space that's not been explored. It's absolutely dependent upon synthesis. So, thank you, Center for Computer Research in Music and Acoustics. Karma. Students, faculty, staff. Students, faculty, staff. Who's the student? Who's the teacher? Often we don't know. There's no distinction. And thank you.